Hello, so let's now continue our discussion about logic circuits and design a different circuit which is also very common in actual practice. So it is a 2-bit comparator. So a comparator does what? So now let's say we have an input X which is actually has 2 bits, X1, X0, and we have an input Y. Obviously they are binary, so this is Y1 and Y0. Okay, so now our 2-bit comparator can be of two types. So one type is that this is my comparator here. So I give it X and I give it Y. Okay, and then it gives us 1 if X is greater than Y, and 0 if X is less than or equal to Y. Okay, now I put an underline here. It's not a vector here, but I put an underline just to distinguish between bits and a bit string or a full number. Okay, okay, so now, and the other kind of comparator we can have is that it can give us 1 when X is not equal to Y, and it can give us 0 when X is equal to Y. Okay, so then this is again our input X and this is again our input Y. So now, since we know the type of outputs we can have, then we can actually make our table here. So now we have 4 inputs here. So we have x1, x0, y1, y0. So then since we have 4 inputs, how many combinations we have? We have 2 to the 4, which is 16 inputs. But then if we are designing, so this is my case 1 and this is my case 2. So now I'm designing case 1 kind of a comparator in which whenever x is greater than y, I get a 1. Okay, now what are the conditions in which x is greater than y? So this means we have 2 bits, right? So 2 bits means that we can have 0, 1, 2 or 3 as the numbers. So then this means then when we have how many cases that x is equal to 1 and y is equal to 0, and x is equal to 2, y is equal to 0 or 1, and then if x is equal to 3, y is equal to 0, 1. Now for x is equal to 1, we get what? We get 0, 1. And for y is equal to 0, we get 0, 0. For x is equal to 2, I get 1, 0. And y is equal to 0, I get 0, 0. Then for x is equal to 2 and y is equal to 1. And for x is equal to 3, I have 0, 1 and 2. So 0, 1 and 2. So these are the only inputs for which my output is equal to 1. Now why we are collecting the outputs of 1? Because these are the minterms we have to find the actual expression. So now let's see whether we can simplify it or not. But first of all, so now let's say I'll write output is equal to. So output is equal to what? So this is x1 bar, x0, y1 bar, y0 bar. So x1 bar, x0, y1 bar, y0 bar. So similarly I can write all of them. So x1, then all bars. So then next one is x1, x0 bar, y1 bar and y0. The next one is x1, x0, y1 bar, y0 bar plus x1, x0, y1 bar, y0 plus x1, x0, y1, y0 bar. Okay. Now let's say we have this. Let's combine this guy, this guy, this guy, and this guy. Now note that here we have x1, y1 bar, x1, y1 bar, x1, y1 bar, x1, y1 bar. So then this means I can say x1, y1 bar times this is what? X0 bar, y0 bar plus x0 bar, y0 plus x0 y0 bar plus x0 y0. Now if I say that this sum is equal to 1, whether it will be correct or not? That will be correct because these are the two inputs and I'm considering all four options of them. Okay, so this is equal to 1 because of this. So I can write x1 y1 bar. So times, I can say here, x0 y0 plus x0 bar y0 bar plus, I can say, x0 y0 plus x0 y0 x0 bar y0 bar bar. So any binary variable ORed with its complement is equal to 1. So this is equal to x1 y1 bar. Okay, now I'm left with two more. I'm left with this guy and I'm left with this last guy. So what can I take outside here? So I can take, probably I can take x0 y0 bar outside. So x0 y0 bar. So then this is then here I get x1 y1 x1 bar y1 bar, and here I can get x1 y1. So x1 y1. So this is my comparator of case 1 here. Okay, so if I draw it, how will it look? So we have input x1 and input y1 complement, right? So then this is, and here then I have x0. I want to do this OR one first, so I can say x1 y1 both inverted. So then this is AND here, and then x1 y1 x1 y1. So this drawing is probably not the best. So then this is ORed here, then this is ANDed with x0 and y0 bar. So then I have x0 and y0. Now this guy is ANDed here, and probably I should end it here as well. So this guy and this guy is ORed here. So this is OR. So this is my output here. Okay, so this is nothing but the drawing of this guy. Okay. Okay, now let's talk about the comparator of a second degree. So in this one, now note that for x is equal to y, this is easier. So I'm going to only uh, collect the terms for which x is equal to y. So this is just 0, 0 and 0, 0, 1, 0 and 1, 0, 0, 1 and 0, 1, 1, 1 and 1, 1. Okay, so for this my output is 0 here, 0 here, 0 here, 0 here. Now note that this is easier in terms of product of sum form. So I will just write my output. This is equal to x1 bar plus x0 bar plus y1 bar plus y0 bar times x1 plus x0 bar plus y1 plus y0 bar times x1 bar plus x0 plus y1 bar plus y0 times x1 plus x0 plus y1 plus y0. Okay, so in this case my circuit looks like this. So I will say my x1 x0 y1 y0. So all are not here. So then this is one OR. Okay, second OR is x1 x0 bar, and then this is like this. So now third one is not here, not here, and the fourth one is no not, see. Okay, so then everything here is x1, x0, y1, y0, all these outputs. So then this and this I have to add. So this is my output clear here. So we have four OR gates because of these four, and then we AND them all to find the final output. So this is it about two kinds of comparators, one in which one input is greater than the other, and the other in which one input is not equal to the other. Okay, so hope it was easy to understand. Thanks for watching. Hope you like the video.